Good morning, students. In this video class, I am going to develop the relationship between heat capacity and entropy. Relationship between heat capacity and entropy. Heat capacity and entropy. Why this relationship is important? Why this relationship is important? See these Maxwell's equations. In these equations, or Maxwell's equations provides the partial derivatives of entropy with respect to volume. Similarly, partial derivative of entropy with respect to pressure. In this Maxwell's relation, there is no information on, or there is no equation for partial derivatives changes in entropy with respect to temperature. There is no information on changes in entropy with respect to temperature. But in thermodynamics process, entropy changes with respect to temperature is an important phenomenon. Hence, to establish the equation between entropy and temperature, this relationship between heat capacity and entropy is important. Okay, heat capacity. Heat capacity. Right. What about the mathematical equation? Mathematical representation of heat capacity. Mathematical representation. Mathematical form of heat capacity. For constant volume process, CV is equal to dou Q divided by dou P at constant volume. For constant pressure process, Cp is equal to dou Q divided by dou T at constant pressure. Clear? Changes in heat content with respect to temperature. Changes in heat content with respect to temperature. This is constant volume process. This is the constant pressure process. This is the mathematical form of heat capacity for both pressure and volume. Second law of thermodynamics says that second law of thermodynamics for a reversible process. ds, changes in entropy is equal to dq by t. Changes in entropy is equal to dq by t. From this information, I can write like this: T ds is equal to dq. I am going to substitute T ds instead of dq on both equations. Hence, for constant pressure process, constant volume process, Cv is equal to T into changes in entropy with respect to changes in temperature at constant volume. For constant pressure process, Cp is equal to T into changes in entropy with respect to temperature at constant pressure. Clear? Clear. For a definite temperature difference, or T1 to T2, this equation becomes ds is equal to Cv by T, 1 by T into Cv into dt, or I can write like this: delta S is equal to Cv into ln T2 divided by T1. Similarly, for the known temperature difference, this equation becomes ds is equal to Cp into 1 by T into dt. Clear? finally, changes in entropy is equal to Cp into ln T2 by T1. This equation is highly useful in estimation of entropy or estimation of changes in entropy in a reversible process with the initial and final temperature are known. This is the equation or relationship between entropy and heat capacity. Clear? In Maxwell's relation, the changes in entropy with respect to volume, similarly changes in entropy with respect to pressure are given in partial derivative form. There is no information regarding changes in entropy with respect to temperature in Maxwell's equation. In order to bring the equation, we must establish the relationship between heat capacity and entropy. The mathematical form of heat capacity is CV for constant volume process. CV is equal to dou Q by dou T at the constant volume. For constant pressure process, Cp is equal to dou Q divided by dou T at a constant pressure. Second law of thermodynamics says that for a reversible process, ds is equal to dq by t. Hence, dq is equal to T into ds, temperature times changes in entropy. Now I am going to substitute dq instead of dq, T ds in the above two equations. Finally, this equation gives changes in entropy in constant volume process under reversible condition. It is Cv ln T2 by T1. Similarly, the changes in entropy for constant pressure process under reversible condition, delta S is equal to Cp into ln T2 by T1. These equations are highly useful in estimation of changes in entropy at two different temperatures under reversible condition. Thank you.